In this video, we're going to look at the use of critical points and inflection points in both graphing a function and optimizing, that is to say, finding the maximum or minimum values of a function. The function we're going to start with is f of x equals x cubed minus 3.5 x squared minus 20x plus 13. The critical point is where the derivative equals 0. X. In order to find this, we need to take the derivative of this function. Derivative of this function will be 3x squared minus 7x minus 20. If we factor this, we find that it equals 3x, x here, 5 and 4. Okay. This tells us that the critical points will be where this function equals 0, which is where 3x minus 5 equals 0 and x minus 4 equals 0. Thus, x either equals 5 over 3 or x equals 4. These are the critical points of the function. If we want to know what the function looks like, we can graph the original function, and we will see that it looks a lot like this, where this point right here, second, I am missing a minus sign up here. I'm missing a minus sign. 5x. Okay. There we go. That's correct. Therefore, our first maximum will be minus 5 over 3. And our minimum will be x equals 4. Notice we set the first derivative equal to 0. The reason we do this is that we want the point where the slope is 0. That only happens when it's either at a maximum point, a minimum point, or what we call a saddle point, which looks something like this, or like this. Because in each of those instances, the slope equals 0 just for a point. We can determine what, analytically, we can determine whether or not we have a maximum, minimum, or a saddle point by use of the second derivative. To find this, we take our equation for the first derivative, and we take the derivative of that. Derivative of this function would be 6x minus 7. We therefore conclude that we set this equal to 0, that the inflection point, the inflection point is where that equals 0, that our point must be 7 over 6, positive. Now, a positive second derivative results in a shape that looks like this. This is when it is greater than 0. When the second derivative is less than 0, you have a mountain type shape. And when it does equal 0, you get a saddle point. Okay. Now, in our function, we have first a arching top, and we have, here we'd expect the second derivative to be negative, less than 0. And over here, since we're getting a valley type shape, bowl type shape, we'd expect the second derivative to be greater than 0. So if it's changing continuously, and it is, we must expect that somewhere in between here for the second derivative to equal 0. According to this value, the point is at 7/6, which is slightly greater than 1. So I would expect that to be about right, somewhere around right here. I'm going to guess, about right there. So 7/6. And we could have graphed this function roughly just from the derivatives, the first and second derivative alone. The second derivative would have given us the shape. The first derivative would have given us where the slope was upward and where it was downward. Also, where the first derivative is 0 would have given us the max and the min. And because this function, the global max of this function is this point, because there's no other maximums that are higher. So you want to go for endpoints. This one may end up getting higher. The global minimum, except perhaps for endpoints, because this function may continue on further down, will be this point right here. We can use of the first derivative to find the maximum of a function is used in many fields. Anytime you need to find the point at which a function is at its maximum amount, and it's continuous, the first derivative has to be 0, because that's where the line, the slope of the function is 0, as when it's at a minimum or a maximum. And we can distinguish between these with the second derivative.